Problem 55b from Reading Assignment 3, Section 6. This is a true or false question. The statement that you need to show to be true or false is like this. It says one possible iterated integral of f over the prism like this is given by this integral here. You can see the prism is going for x from 0 to 1, y from 0 to 3x minus 3, and z from 0 to 5. And the integral has y going from 0 to 3x minus 3, x going from 0 to 1, and z going from 0 to 5. Now, this statement is actually false. So let me explain why. Here is why. You see that this part, we are integrating a function of x, y, and z over z. Bounds are constant, so we end up with a function of y and z, x and y. So we kill the dependence on z, and then here we're integrating this guy over x between two constant numbers, so we end up with a function of y. So we kill the dependence on x, we end up with a function of y, and then we integrate over y. So we kill the dependence on y, but because the bounds are functions of x, one of the bounds, we end up reintroducing the dependence on x. So this isn't correct, because let's imagine that f is a density function. So density as a function of position, measured in kilograms per meter cubed. And I ask you, what is the mass, so the integral over the volume of this density over this prism? And if you tell me that the mass of the prism is equal to something like x squared or x cubed or sine of x, then this wouldn't be very meaningful, because x doesn't exist outside of this integration. So let me elaborate a bit more. So outside, position is not meaningful. Once you are inside of this integral, you have a meaningful y. So let me highlight this. So here, y has a meaning. So y has meaning. But because y is just a dummy variable, outside the integral, it just disappears. It's kind of like when you're writing a for loop, if you're outside the for loop, it's not really like this variable that stands for the for loop counter either doesn't exist or doesn't really mean what you want it to mean. Then once you move further into the integral, here, x starts to have meaning. So here, x has a meaning. And then inside this innermost integral, finally, all three variables have meaning. And I can't highlight it. Okay. Okay, how should I deal with this? Okay, I'll use, I'll just circle it. So when you're inside of this, then all three variables have meaning. So z has a meaning. Now that's not the only reason why this is a false statement. You were also given a flawed description of the region. Here is why. Let me draw this prism that this is describing. Let me first imagine that z equals 0, because nothing really depends on z here anyway. So just to help me understand, let me set z equals 0 and understand which points on the xy plane at least satisfy this these inequalities. Now you see z equals 0 does satisfy this inequality here. So then this is sort of like the lowest triangle in this prism. X needs to be between 0 and 1. Okay. So we have 0 and 1. Z needs to go from 0 to 3x minus 3. 3x minus 3 is like this, where this is negative 3. So this would be y equals to 3x minus 3. Sorry, actually, I'm not quite drawing it correctly. Okay, so 3x minus 3 would have negative 3 as the y-intercept. And a slope of 3, right? But then look at what this is saying. It says greater or equal to 0 and less than or equal to this. But that's not possible. It needs to be greater or equal than 3x minus 3, right? So actually, the correct way to write this is to swap these two things. Now, if you write it like this, then it's going to be better. So you'll have x between 0 and 1, okay, and then y between this line and this line. So this would be this triangle, but that's not the prism. This is just the part of it on the xy plane. But let me still draw this. So we have x going up to 1, and y would be negative, and there would be this point negative 3. So this is the part that I sketched. And now we know that z would go between 0 and 5. So we would just need to extend this like this all the way up to z equals 5. And now if you want to write the correct integral, what you'll need to do is you can keep the bounds that we had. You don't have to redefine them. But what you need to do is to, let me actually highlight this so you can see it better. Okay, so this is how it's going to look. So it's like cheese. Okay. So the correct integral can have the same bounds as before, but let's just make sure that the order is written in a correct way. So you see here I put 0 to 1 bounds on x, so those would be constant. Then bounds on y would depend on x, which is fine because here x is meaningful. Remember, x is meaningful when we move past the x integration. So then this is fine. And then you see how I swapped the two? We have 3x minus 3 to 0 so that we have the correct order. This is actually the lower number. This is the higher number. And then z would go from 0 to 5. It's not the only possible way to integrate this, but this is one valid way to do this. The question I want to do is question 54 in Reading Assignment 3, Section 6. But before I do this question, I want to convince you of something. This is the fact that equation of upper hemisphere of radius A is given by this equation. The equation is z equals to square root of a squared minus x squared minus y squared. The reason this is the case is because we can start with the equation of a sphere. So x squared plus y squared plus z squared equals to a squared. Here the radius of the sphere is a. Then from here we can solve for z. So we get z, so x and y all go to the right hand side. And okay, let me actually solve for this. So we have a squared minus x squared minus y squared. And next we solve for z and we get plus or minus square root of a squared minus x squared minus y squared. Now the plus will give you the upper hemisphere and the minus will give you the equation for the lower hemisphere. Now let's move on to the actual problem. The problem asks to find the average z-coordinate of points on and within a hemisphere of radius 4 centered at the origin with its base in the xy plane. So the hemisphere would be like this. So this is the base. This is this top dome. So it looks something like this. This is the region, let's call it V, or the volume of this region would be V. The radius is 4. And we want to find the average z-coordinate. By definition, average value is the integral, average value of some function f is the integral of the function f divided by the volume, by the total volume. And volume can be computed by integrating 1 over the volume of the region. Now let's guess what the answer could be. You see that the maximum it can be is 4, the minimum it can be is 0, probably it's somewhere in between. We know that it's probably not 2 because there is more points with z-coordinate smaller than 2 than points that with z-coordinate greater than 2. So we know that it's probably going to be around 2 but less than 2. Turns out the answer is 1.5. Let's find the answer and see that the guess was correct. First, let's find the integral here in the numerator. So this would be the integral of the function f, which is equal to just z in this case. To get this integral, we need to figure out the bounds of integration. I chose the order dz, dy, dx. So let's, and the integrand is z. So the approach I'll take to figure out these bounds is I want to sort of create a hemisphere on this figure by choosing the correct bounds for x, y, and z. Let me start from the outside. I'll choose the bounds between -4 and 4. So x would be at most 4 and then at least -4. For every value of x, I want to describe the semicircle. I want to actually describe everything inside of this circle here. So I will describe the bottom semicircle first. So I will say negative square root of 4 squared minus x squared. The top semicircle would be square root of 4 squared minus x squared. So integrating like this, if I don't look at this integration, what I'm essentially integrating over is this base of the sphere. Now, for every value of x and y in this circle, I need to create the z values. I need to go over all of the z values that will sort of traverse everything inside of the hemisphere that we're talking about. So we know that the bottom of the hemisphere is at z equals 0. So for every value of x and y, we would start at z equals 0, and then we would go up to where? Well, to the surface of the hemisphere, right? And what was the equation of the surface of the hemisphere? This top surface. It was z equal to square root of 16, remember this a squared, minus x squared minus y squared. So this way, we are integrating over these sort of little parallelepipeds here, creating this entire shape. So this would be from 0 to square root of 16 minus x squared minus y squared. I think the way you were explained this was a little bit different. It was more in terms of bounding surfaces. So let me explain it this way as well. Or let me more just show you that it's all consistent. It gives you the same result. But first, let's do a sanity check. Outside bounds are constant. Everything is fine. These bounds depend only on x, which is also fine because here x exists on this integral. And this integral can be anything. So these are functions of x and y, and this is allowed. Now let me redraw this hemisphere and show you that the bounding surfaces are correct. So we have this guy like this, base of the hemisphere, top dome of the hemisphere. So this is saying that one of the bounding surfaces is 0, z equals 0, and that is correct. Z equals 0 is indeed a bounding surface. Another bounding surface is the upper dome of the hemisphere. This is also fine. That's sort of how we set it up anyway. Then there is this bounding surface, the bottom red one. This is parallel to the z-axis because it doesn't involve z, and it gives you sort of a semicircle like this, but it's a surface, right? So it looks something like this. No. So it goes like this. So it very snugly fits this dome. So it doesn't allow you to integrate anywhere past this dome. The other bounding surface is this blue one. This is like this. Oops. And then here it's like this. So you see, these two bounds on Y describe a cylinder like this. And now the bounding surfaces for X are just two planes that are vertical. And those would be at X equals -4 and at X equals 4. So if you prefer drawing the bounding surfaces first, then this is fine. Or if you prefer this way of thinking where you create a shape from scratch, this is also another way. And you can think of it as going from the inner integral outwards, or you can start with the outer bounds and then think inwards. That's what I did here. Sometimes I use both methods. I'm not really sure which one's better. On this slide, I copied what I had on the previous slide. You can check that I didn't change anything. On the next slide, I used the fact that a hemisphere is made up of 4 parts. Let me show you what I mean. So we have a hemisphere, and I split integral over this hemisphere into 4 parts. The 4 parts are split essentially by planes x equals 0 and y equals 0. And then, yes, and this one. And you can see that no matter which part I'm integrating over, I have the same value for the integrand. So if I have some point in this portion, in this segment of the volume, it's going to have the same value of z as a corresponding point in any other of the 4 segments. So I can take the integral over just this part, and then multiply it by 4. Now, you should realize that this only works if I'm integrating z. If instead I was integrating y or x, I wouldn't be able to do this trick. I mean, not exactly this trick, because, for example, in this portion of the volume, the value of, say, y is different from this portion of the volume. So this only works for z. And you can check, if you're not convinced, you can try to integrate over all 4 parts, and you'll see that the answer for each of those parts is going to be the same. So now the integration for x will go from 0 to 4. For y, it will go from 0 to this square root of x. So this would be y going from 0 to the square root of 16 minus x squared. And then z would go from 0, okay, upwards. Then let's integrate over z. Here I get antiderivative, which is z squared over 2, from 0 to this big square root. Next, I'm evaluating it at the endpoints. This guy, when you square it, what you get is just the inner part of this square root. So you get 16 minus x squared minus y squared. And then, let me highlight it. So you get this part without the square root. And then this 2 stays here, this 2. 4 stays here as is. Next, what I did is I integrated over y. For this part, as far as the y integration is concerned, this would be a constant. So what I got is this. First, by the way, I canceled 2 and 2 here. Then I integrated over y, so this guy is a constant, so I get this times this. So these two brackets are these two brackets. And then minus antiderivative of y squared would be y cubed over 3 between the endpoints. And then I am going to write this as this. You see how this guy is equal to, this whole thing is equal to 1/3 square root of 16 minus x squared to the power of 3, and this guy is equal to square root of 16 minus x squared to the power of 3. So then I have this minus this, so I get 2/3 of this guy. That's how I got this 2/3. So I have 2, here I have 2/3, and then I have this square root cubed dx. Next, I simplified this a bit, so I combined this 2 and this 2. I got 4/3, this integral. Next, I need to integrate this. Whenever you see square roots like this one, what you can do is to use trigonometric substitution. I like to think about trigonometric substitution geometrically. If you don't like this method, that's okay. You can use trig substitution whatever way you like. So the way I think about it usually is this way. I imagine that u is an angle like this. Then x, and that this guy is equal to 4. That's what I got from 16 by square rooting it. This way, what I get is this. I get that x is equal to 4 sine u, and that cosine of u, 4 cosine of u is equal to square root of 16 minus x squared. So this way, this guy is 4 cosine u. So then I get this. Okay, so bounds on x with this trig substitution are converted from 0 to 4 to u going from 0 to pi over 2. The reason why is because x needs to go from 0, so this would be that case. That's why I have u equals 0 to x equals 4. This is what happens when u increases all the way to here. That's when x becomes equal to 4 and u becomes equal to pi over 2. Now, as I discussed, this square root is 4 cosine u. That's what I have here. Or you could just plug this in and use trig identities to get this as well. Dx is equal to 4 cosine u du. So then when I plug this all into here, I get this. I have 4 over 3 stays as is. Bounds go, instead of 0 to 4, become 0 to pi over 2. That's what I got from here. Then I have this square root cubed. And then I have dx. Next is simplifying this. I got 4 cubed. This makes it 4 to the 4th, and this makes it 4 to the 5th. That's what I got here. 3 stays as is. We have integral 0 to pi over 2. Then we have this cosine, and then cosine cubed, which is cosine to the 4th, which I can write as cosine squared and then squared again. The reason I wrote it this way is so that I can use this formula for cosine squared u. Remember, cosine squared u is equal to 1 plus cosine 2u divided by 2. Square stays as is. Then I expanded this using the formula for I guess, binomial formula. Also, I used the fact that 2 squared is 4, which canceled with one of these 4s. That's how I got this to be 4. Next, what I did is I used double angle formula on this guy. So I got 4 plus cosine 2u over 2. Sorry, not 2u, 4u, because now it's 2 times 2. That's what I have here. In the next step, what I did is I simplified this 1/2 plus 1, which gave me 3/2. The rest stays the same as is. Then I integrated, so I got 3 over 2u plus sine of 2u. You see, when I differentiate, I'll get cosine 2u times 2. And then plus cosine becomes sine 4u divided by 4. No, sorry, there should be a 2 here. Okay, I'll fix it in the main notes. Okay, so then we will have this. Plugging in pi over 2, we will get, actually, let me just plug in 0 and pi over 2 here. You see, if you plug in pi over 2, you're going to get pi. So this is 0. If you plug in 0, you again get 0. So this is gone. For this one, you'll have pi over 2 times 4 gives you 2 pi. So then this is 0 again, and at 0, it's also 0. So this is 0. Then you have only this guy left, so you have 4 to the 4th over 3 times 3 over 2 times pi over 2 minus 0, which is pi over 2. So you have this. Then you can cancel one of the 4s with this 2 and 2, which gave you 4 to the 3. 3 cancels, so you have 4 to the 3 times pi, and this guy is gone. Now let's move on to finding the volume of the region. Remember, the region was this hemisphere. Volume of a hemisphere is half of the volume of a sphere. So we have 4 over 3 pi times r cubed for a sphere. For a hemisphere, we divide it by 2. So we get 2 over 3 pi 4 cubed. Now, if you don't remember the formula, you can just carry out this integration. It will be the same as the integration I'm showing here, but the integrand would be 1 instead of z. And then, sorry, 1 second. And then, to find the average, you need to divide the integral of z by the volume. So you get this guy over the volume, this guy. So you get 4 cubed is cancelled, pi is cancelled, so you get 1 over 2 over 3, so you get 3 over 2, or 1.5, which is exactly what we guessed. Question 61 in Reading Assignment 3, Section 6. The question asks you to use a triple integral to compute the volume of the pyramid with vertices 0, 0, 0, 2, 0, 0, 2, 2, 0, 0, 2, 0, and 0, 0, 4. So then the pyramid would look something like this. This side, on the back there would be this edge that I'm showing you, this edge, and then the base would be a rectangle, and there is also this edge. This pyramid has 5 sides. The 3 sides that are parallel, that are aligned with the x, z, zy, and xy planes are easy. The more complicated ones are the slanted surfaces. And what I'm doing here, I'm trying to find the equations of these surfaces. If you see, if you're comfortable using any sort of shortcut to get equations of these 2 slanted surfaces, you can go ahead and do it. Just make sure you're doing this correctly. I'm more comfortable just going brute force and figuring out the normal vector to each of these surfaces, and then figuring out the equations of these surfaces from there. So the red surface that I highlighted, let's call it surface 1. I'm going to use this vector to find the normal and this vector to find the normal. So this first vector is 0, 2, 0. This is what I wrote here, 0, 2, 0. Second vector has x component of -2, y component of y component of 0, and z component of 4. That's what I wrote here. When you find the cross product, you get I hat times 2 times 4 minus 0 minus j hat times 0 minus 0 plus k hat 0 minus -4. So then you end up with 8, 0, and 4. A point that lies on the plane, for example, we can take 2, 0, 0, this point. And then from there, we can find the equation of the plane using 8, 0, and 4 from here. and using this point 2, 0, 0, setting this dot product to 0, and then expanding. First thing I did though is divided the left-hand side and right-hand side by 4. That's how I got 2 here. This part is gone, and here I get 1, so I get this z over here. And then I expanded it to get 2x plus, well, 2x minus 4 plus z equals 0. Transferring 4 to the right-hand side, I get this equation. So surface 1 has an equation of 2x plus z equals 4. Now let's figure out the other surface. This would be surface 2. I'm using a vector 2, 0, 0. And 0, negative 2, 4. This would be this one. So x component is 0, y component is negative 2, and z component is 4. Then I get I hat 0 minus 0 minus j hat 8 minus 0 plus k hat negative 4 minus 0. So this gives me 0, negative 8, and negative 4. And I'm using a point 0, 2, 0, this point. Then I get 0, negative 8, negative 4, 0, negative 8, negative 4, and the point 0, 2, 0, these here, set it to 0. Then this goes away, and I divided by negative 4, which gave me plus here and plus here, and this became 2, and this is gone. That's how I got 2y minus 2 plus z equals 0. Then I expanded it, so I got 2y minus 4, brought 4 to the right-hand side, and I got this equation. So then the blue surface has an equation 2y plus z equals 4. Now let's set up the integral. I will set it up using the concept of bounding surfaces. So we need 6 bounding surfaces, and we need to be careful that the bounds of integration have correct dependencies, meaning that outer bounds should be constant, inner bounds should only depend on this outer variable, and the innermost bounds can be anything. I will try choosing the order dx, dy, dz. Turns out it is a good order. Sometimes the first order you try is not very good. I actually tried the order with z on the innermost integral first, and it didn't quite work for me. So let's choose this one. Then the bounds on x. Actually, I shouldn't be using blue. Just give me a second. Let me erase this and use neutral color. Okay, so x, y, z. The bounds on x would be, let's see here. Let's make the bounds, sorry. Let me first choose the lower bound on all of them because this is the easier one. I know that the surfaces x equals 0, y equals 0, and z equals 0 are 3 of the surfaces that we would want to have. So this would just make this sort of corner, create this corner. And then, so I guess these would be that, this, and this, then we would want to have the upper surface on X. Let's make it, well, we could take this one as the surface on X. Let's rewrite it so that we can write X in terms of Z. So we have 4 minus Z over 2. So we will have 4 minus Z over 2. This would give us this surface. Then Y would be bounded by 0, and then this blue surface here. This, if you solve for Y, this would give you Y equals 4 minus 2Y, sorry, 4 minus Z over 2. So we have 4 minus Z over 2. This would be this surface. And then the last surface, well, is the surface on Z. But you see, we already selected 5 surfaces. And we know that the original pyramid had 5 bounding surfaces. So the 6th surface, the one on Z, should be just chosen in a way that doesn't mess things up. So we want to make it at Z equals to 4. Because if we make it any lower, we will end up chopping off a portion of this pyramid. And if we make it higher, we'll just end up integrating over really nonsensical parts of R3 space. Like, you can try choosing higher value of Z to truncate this, you'll get a really nonsense result. Okay, so the top surface would be Z equals 4. Because really is the only thing that makes sense to truncate. So it would be right here. So just taps it off where the pyramid ends. Now, another way to think about it is, oh, sorry, one thing really important. So I set it up just sort of figuring out the equations of all of these surfaces, but now we need to check that the dependencies are correct. So here we have constants. These are fine. Here, this is fine. This depends on Z. That's okay, because here Z is defined already. And the innermost integral can be whatever. So this is fine as well. Now, the other way to think about it is by thinking, how do we create this pyramid? By first sort of spanning out all values of Z and Y that end up being taken by points in this pyramid, and then creating the X dimension by figuring out what values X takes on. So here, what we would want to do is we would want X and Y to take on these values, which would be from Z equals 0 to 4, and from Y equal to 0 all the way up to Y equals to 4 minus Z over 2. You can verify that this, well, I got this from basically from here, or, you know, from the equation of this blue surface here. Or you could also figure out the equation of this line. You know that it would be well, you would have 2 as the y-intercept. So this is 2 minus Z over 2. So slope in terms of y would be given by 1/2, and it would be negative. So when z increases, y needs to decrease, and then that's how you get this line. Then you could think, okay, which values of x do I want? I know that I would want to integrate sort of like this here all the way to this line. Then for other values of y and z, I would want to integrate from the points on this back plane up to the red plane that we found. So the red plane would be this one, 4 minus z over 2 equals to x. So that's another way to think about it. You can choose whichever way you prefer. Okay, so now let's actually integrate. Here I copied what I had on the previous slide. The next step is to integrate over x. 1 is just a constant, so we get this guy minus 0. So here you see 4 minus z over 2. Everything else stays the same. Then we integrate over y, and we get, well, since this is a constant with respect to y, then we just get this times this minus 0. So really, we just have this guy squared. This is what I wrote here. Then I factored out this 2 and this 2, so I got 1 over 4. Whatever is here, I expanded it, so I got 4 times 4, 16, minus 2 times 4 times z, so minus 8z, and then plus z squared. Then I integrated this, and I got 16z minus 8z squared over 2 plus z cubed over 3. And I plugged in 4 and 0, so I got 16 times 4 minus 8 times 4 squared over 2 plus 4 cubed over 3. And then the same thing evaluated at z equals 0 is just 0. Then I got the following. There's a whole bunch of ways to simplify this. You can do 1 over 4, 16 times 4, minus 8 and 2 partially cancel. So we get 4 cubed plus 4 cubed over 3. This is 4 cubed, and this is 4 squared times 4. So actually these two quantities are the same, so they cancel. And then we're left with 4 cubed over 4 over 3. So we get 4 squared over 3, which is 16 over 3. Problem 33 from 16.7 gives you this integral here. It's a double integral over a region R that's a parallelogram bounded by these 4 lines. Let me sketch what those lines are. We have y minus x equals 1, which we can also write as y equals to 1 minus 1 plus x. This gives me a line like this. We have this equals 1. So this would be a line, the line y minus x equals 1. We have the line y minus x equals 2, which is the same thing as y equals 2 plus x. It would be this line that's parallel. Oops, I missed. This y minus x equals 2. Third line is y plus 2x equals 0, or in other words, y equals to 2x, sorry, negative 2x. So this would be like this. It's aligned with the slope negative 2, like this, and like that. This is y plus 2x equals 0. And then we have y plus 2x equals 4, or y equals to 4 minus 2x. So this would be, well, something like this, 4 minus 2x. So this would look something like this. So y plus 2x equals 4. So then the region is this parallelogram right here. Now the way the question is written immediately suggests a transformation that we could use is u equals y minus x. This way this would become u. And then v, y being y plus 2x, this would make this guy v. This will make a really nice transformed region because in this way, the line y equals 1 plus x, it's this black one, becomes u equals 1. So it's just a straight line. This line becomes u equals 2. The blue line becomes v equals 0. And the green line becomes v equals 4. So then the region is just a rectangle that's parallel to the u and v axes, and that makes it much simpler to integrate, unless we messed up the integrand. So let's check if that's the case. Let's check that the integrand is also okay. So you see, y minus x is equal to u, and y plus 2x is equal to v. So actually we're simplifying the integral, so that's nice as well. If you can simplify both the region and the integrand at the same time, that's the best transformation you can get. Or sometimes maybe you'll just have to be happy with simplifying one of them. And this, using the notation from the lectures, is S. Now, in order to get the Jacobian for this transformation, we need x and y in terms of u and v. So far, we have the opposite, right? So let's get what x and y are. We can subtract these two guys. Let's subtract v minus u. Then on the right-hand side, we'll get y plus 2x, and on the left-hand side, sorry, and we're subtracting this, so y cancels, and then we get 2x plus x. So then x, which is the same thing as g of uy, or uv, equals to v minus u over 3. To get y, we can, for example, we could, let's say, use this one. We could write y as u plus x. So then this is equal to u plus v minus u over 3. This is equal to 3u plus v minus u over 3. equals to 2u plus v over 3, which gives us y equals, which is equal to some function of u and v, h, equals to 2u plus v over 3. Now let's evaluate the Jacobian determinant. First, we need the Jacobian matrix. It's given by these partial derivatives. You see in the first row we have everything corresponding to x, and in the second row we have everything corresponding to y. The reason I'm saying it is because g is here, this g, and h is here, and then columns correspond to u and to v. Now let's evaluate the derivatives. Partial g partial u is negative 1 over 3. Partial g partial v is 1 over 3. Partial h partial u is 2 over 3. And partial h partial v is 1 over 3. To get the determinant, well, let me write, oops. We do negative 1 over 3 times 1 over 3 minus 2 over 3 times 1 over 3. This is equal to, let's factor out 1 over 9, then we're left with minus 1 minus 2. Then we have negative 3 over 9, which is negative 1 over 3. Next is to actually set up the integral and evaluate it. For the integrand, we determined that it was u over v plus 1 to the fourth. That's what I wrote here, u over v plus 1 to the fourth. Now, those, you see, there is, we need to write correct differential area, and the correct differential areas would involve Jacobians, the magnitude of the Jacobian. So this would be absolute value of one. So it's absolute value of the determinant of the Jacobian matrix. So it's this guy. And those guys would be areas of infinitesimally small parallelograms on in the region R. So let's just call it tiny areas of tiny parallelograms. Those tiny parallelograms correspond to rectangles on this plane. So when this guy makes this rectangle of size du times dv, what happens here is there will be some parallelogram that ends up being described, spanned, that corresponds to this, and its area would be given by absolute value of the Jacobian determinant times du dv. I'm not deriving this, it's just a reminder. Okay, so then we need bounds on u and v. Those would be 1 to 2 for u and 0 to 4 for v. Now this Jacobian determinant absolute value is the most important probably part not to forget. So just, I don't know how the marking will go exactly, but I can guarantee that there's a lot of marks allocated for, you know, first of all getting the Jacobian, but also not forgetting to plug it in. So if you completely miss these steps, then it's not gonna, like, it's important. It's important that you put this here. Okay, so this absolute value is equal to 1/3. I wrote it over here. Then we have what? Then I separated the integral. So everything that corresponds to u, I wrote in the first integral. And everything that corresponds to v, I wrote in the second integral. You see this, it was in the denominator, that's why 4 became a negative. And then we have this. Next, I was integrating, and I got 1/3, and then this guy became u to the 5th over 5 from 1 to 2. This guy became v plus 1 to the power of -3 over -3 from 0 to 4. The denominator became 45, and then this negative is here. 2 to the 5th is 32. Then I have -1. Then here I have this guy. This is 1, this is 5 to the -3 minus 1 to the -3. That's what I have here. And 5 is coming from 1 plus 4. Then this is 125. So this whole thing is 125 minus 1, sorry, yes. My bad. This whole thing is 1 over 125 minus 125. So then that's how I got 124, except this should be a negative, but I combined it with this negative. Let me just write it. 124 over 125, negative became a positive. Then I have 32 minus 1 gave me 31. I have this 45, and then this 125 from here. And then you can work out the long multiplication, but I'm skipping the steps, and the answer should come out to this. Problem 47 from 16.7, you're asked to evaluate the Jacobian for the transformation from spherical to rectangular coordinates. And this transformation is like this. Let me remind you why this transformation makes sense. Let's draw some point. Remember, angle phi is this angle. Angle theta is the one you get by projecting this onto the xy plane. And then you get, well, this is 90 degrees. And this is angle theta. And rho is the length of this segment. Now, you have this factor here for x and y. This comes from the projection operation. This length is equal to rho times sine phi, because, well, not very well drawn. Because this length is rho sine phi. Then we have this projected on the x-axis is going to give us cos theta, and for y-axis is going to give us sine theta. So this will give us sine. Now for z, we're going to get rho cos phi, because that's what you get by projecting on the z-axis. So this rho cosine phi. And the question asks you to show that this Jacobian is rho squared sine phi. Now, again, as you heard in lecture, there is a bit of confusion because sometimes Jacobian is the Jacobian matrix and sometimes is the determinant of the Jacobian matrix. Well, here they mean the determinant. But I'm just going to use bold case J for the matrix, and determinant of bold case J for the determinant. Okay, so J is given by this matrix of partial derivatives. Again, in the first row, we have everything for x, then everything for y, then everything for z. And then here we have derivative with respect to rho, with respect to phi, and with respect to theta. With respect to rho, we will get everything the same except rho will go away. So we'll get sine phi cos theta, sine phi sine theta, and cos phi. For derivative with respect to phi, we will get rho cosine phi times cosine theta, rho cosine phi cosine theta. Then we have rho cosine phi sine theta, rho cosine phi sine theta, and then we have negative rho sine phi, negative rho sine phi. With respect to theta, we'll have rho sine phi, and then negative sine theta. That's what I have here, and negative moves outside. For y, we'll have rho sine phi cosine theta, rho sine phi cosine theta, and then here, with respect to phi, this derivative is 0. Now, I should have emphasized this Jacobian is function of, well, x, y, z is a function of rho, phi, and theta. That's why I'm differentiating like this. Okay. Now, there is the way that you're probably expected to do this is to just brute force evaluate the determinant and simplify it as much as possible, which you probably should do just to get some practice with determinants and trig identities. But I just thought I'll teach you a trick, or maybe you already know it. Anyways, so you'll notice that this column has factor of rho that's in common, and this column has rho, and well, this is 0, and then sine phi. So what I'm going to do is I'll use the property that if you have columns of the matrix multiplied by something, what you can do is you can factor out those things that are multiplying the columns and take them out of the matrix like this. So that's what I did. I took this row. You see rho multiplies this entire column. It's kind of like this B. And then there is a rho sine phi also. So then you get rho squared sine phi. And then this rho squared sine phi is here. And then next we have the determinant of everything that's remaining. So then you see this column stays the same as this one. This one is the same as this except without rho. And this column same as this one except without this highlighted stuff. So now we just need to evaluate this determinant. So you see I have sine phi cos theta, and then I have this determinant. So this guy gives us 0 minus this product, but with this minus it becomes a plus. So we have plus cosine theta sine phi minus this times this product. This gives us 0. This gives us negative cosine theta times cosine phi. And then we have negative sine theta times this determinant, which gives us sine squared phi, sine theta with a negative, minus cosine squared phi, sine theta. Then we have rho squared sine phi, rho squared sine phi. Then we have sine squared phi, cosine squared theta. These negatives cancel, and we have cosine squared phi, cosine squared theta, plus, so the way we got plus is from this and also this. You see these cancel. We get plus. Let's see. What I did here is I actually simplified using the fact that sine squared phi plus cosine squared phi is equal to 1. So this sine theta comes out of this bracket, and then we're left with 1. That's how we got sine squared theta. Oh, sorry, never mind. I did this on the next line. Here I just expanded, I think. My bad. Okay, so then basically we have this is just going to be sine squared theta. This whole thing is sine squared theta. And then on the next line, I used the following. On the next line, I took this cosine squared theta and factored it out, and I simplified this sum to be 1. So I got cosine squared theta, and this plus sine squared theta is here. This whole thing is 1, so we end up with rho squared sine phi, which is what we wanted to show.